Hello everybody, welcome to my class. Today I am going to discuss about the proofs of unbiased estimators of population mean and the variance by their samples information. What does it mean that? For example, if I use part of the data, part of the population which is called the sample, and if I calculate sample mean, and by dint of the sample mean, if that sample mean can give the information about the population mean from which the sample has been drawn out from, and in that case, if that sample mean gives the value of population mean, it means what you can say that the sample mean is an unbiased estimator of the population mean. So firstly, suppose that x bar is the sample mean and you can suppose b or s squared also, b or a small s squared as sample variance. Sample variance, and you know that the population mean, that the population parameter from which we supposed to draw this sample, the population mean, if you say, the population mean is represented by mu, and the population variance is represented by sigma square. Okay, so in this case what we are going to see whether the sample mean can give the value of the population mean from which the sample has been drawn, and also from the same sample we check that whether or not this sample variance is the estimator of the population variance, which is sigma square. Okay, let's see now. Here we see expectation of x bar. If each item in the sample has same chance of being turned up, then the probability value for each x will be 1 by n, otherwise it will be f by n. Because we have used the probability over here, that means we are predicting the information for the population based on the sample data. Alright, that means expectation of x has been found as arithmetic mean, but as we have used the probability and each x happens according to its chance of being turned up, that means this is a case of random sampling. Alright, and in that case, due to this probability sort of thing, what we have done actually that on the basis of sample we have predicted the information of the population. Therefore the population arithmetic mean is now denoted by mu. And similarly, what we see here, if you take the x bar, sample mean, whether or not the sample mean is the estimator of the population mean, mu. So in this case, what you see, expectation of x bar means, just you can write here like that, summation of x by n, or for the individual series, if this is discrete series, you can also write x bar equals to summation fx by n. So in this case, you see that value of n is total of frequency, but here in this case the value of n will be only summation. So now as this is constant term, so it will be taken out. So expectation of, you have now summation of x equals to 1 by n. Expectation of, there are many x, you can see, that's why you can write here x1 plus x2 plus, if there are sample of size n for example, so on up to xn. So after that what we see, this is 1 by n, and insert this inside, it is expectation of x1 plus expectation of x2. So you can see here, you should have first the knowledge of this sort of distributing this expectation to each item before you understand this sort of thing. So here expectation of x1, x2 and plus so on, plus expectation of this is xn. Alright, and this is 1 by n. What you can write for each x1, like it is expectation of x1 is expectation of x plus expectation of x plus so on plus expectation of x, because if you say x1, x2, x3, xn, these are the individual information, but if you are expecting some sort of information based on the probability for the same population, that means that population has the same mean. So one population has only one mean as in birth. Therefore, if you are expecting about the population mean, that means even through x1, x2, xn you can expect the population. Therefore, in each case you see that expectation of x mu, just like here, it is mu as many time, how many time here? N times mu. So that what you see 1 by n and times how many mu, because we have taken here the n number of terms, so there are n mu, so you can write here n mu. Now this is in the numerator and denominator cancel out, and then it is now mu. So what can you say here in this case? You can say therefore x bar, the sample mean is an unbiased estimator of the population mean mu. Okay, that means you can write mu cap, that means the estimated value of mu is x bar. So if you find the arithmetic mean from the sample, that means that sample mean also represents the mean of the entire population. This is the reason why we see that we can say x bar, the sample mean is, you can write here sample mean is an unbiased estimator of the population mean. Here also you can see that whatever is x bar, we have got mean value. That means x bar in this case and the mu for the population data both are the same. Therefore, you can say that the sample mean is an estimator of, unbiased estimator of the population mean. And if you write mu cap represents that this mu value is estimated value. In this case, obviously, this is from the sample of that population. So, what we saw here, that expectation of x bar equals to mu, that is, you can also write mu cap equals to x bar. Now let's talk about the variance of x bar. What happens here? So you know that the variance of x equals to expectation of x square minus expectation of x whole square. Yes, and this is also can be written as expectation of x square minus the mu square, because expectation of x is mu. Okay, and this sort of term is represented by sigma square. So therefore, saying either Vx or sigma square are the same thing, because based on this this variance is based on the probability. Probability means it is predicting the information about the population. That means whenever you see this variance through the sample data x, for example, then the results will be the result for the population data. Alright, therefore you can write here that V sample value x equals to the population value sigma square. That is the variance of the population. So here in this case, let's apply that again. We use individual series for the easy derivation. So summation of x you can see here, summation of x bar you can see here, summation of x bar by n. And by the variance formula, you know that if you take out n from here, this bracket of this variance, what happens? It becomes 1 by n square, because whatever constant, if you take it out, it will be a square because of the nature of variance of this square. It can also, it is remained here now, summation of x inside, and then you have variance of What you see here, that means it is 1 by n square. Variance of this is x1 plus x2 up to term n we are taking here. That means what we have in this case is, like this is 1 by n square. Now again you have it is vx1 plus vx2 plus so on plus vxn, and because these v's are based on the probability thing, that means each of this is focused towards representing the population, and you know that Vx is the sigma square. So even if you predict through the sample x1, x2, x2, you are predicting the variance of the same population, and one population has only one variance. So what you can write here, 1 by n square times it is sigma square dot 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 up to sigma square. Because this is the same population. Alright, if that will be different, then we write sigma 1, sigma 2, sigma 3 square like this. So you see here that now n square times how many sigma square? It is n sigma square, n times of sigma square, because they are the n terms over here, and then this n and this square has been cancelled out. So what we have got here, sigma square by n. Okay, so this way what you found is that variance of x bar equals to not the sigma square, but in fact this is sigma square by n. So it also follows that, for example, you see, if x follows, for example, normal distribution with mean mu and sigma square, then you can say that x bar follows normal distribution with the same mean, because you can see that x bar is unbiased estimator, same mean, but in this case sigma square becomes sigma square by n. Now you have already seen that expectation of x bar is mu, that means the sample mean is the unbiased estimator of the population mean, and then vx bar, this is not the expectation, but this is the variance of x bar is sigma square by n. Now we see that whether or not also expectation of the sample variance B is the unbiased estimator of the population variance sigma square. Alright? So here this can be represented by, for example, sometimes a small s, but here I am representing this by B and equals to 1 by n. So for the discrete series, if I take, then this is f x minus x bar square. All these are sample information over here only, and if you break it, then it will be like f x square over n minus it is x bar square. So what we are going to see, by this formula or by this term, can you expect the value of sigma square, that means the population variance, that we are going to check here. So firstly, what you see, like expectation of V means, you can write here expectation of the same term over here, as 2 or 3 or whatever number n, this term is variable. If that will be constant term, we could just write it as x bar square. But here, if we focus this to the sample, this x bar is the variable x bar, because for the different sample size, you will see that there are the different sample mean, not the single sample mean. So therefore, for each sample set, this value x bar is variable, therefore we keep them inside this bracket. We cannot write just like here, like x bar square, free of this expectation. Then what you write next then, expectation of summation of fx square by n, and then minus, just you use the expectation formula. Expectation is summation of xpx, just earlier we are seeing. So here it is summation of x bar square and then the probability of this x bar, probability of this x bar. So in this case, you can also call like this, expectation of summation of fx square by n, and then minus we have summation of x bar, and then this is probability for x bar is how many times the sample first is maybe f time in general by f by n. So f by n is the probability for that. Also you can write summation of fx bar by n. So because this is a square, so you have to put here a square. Okay. Now let's talk about how to get these two terms. If you find these two terms and if you put it there in the form of mu and sigma square, then you will see that whether or not this sample variance is going to estimate exactly the population variance. So from you have variance of x equals to sigma square, and variance is also summation by fx square by n, and because this is based on the probability, so it will give you mu square. Okay, and that is equals to sigma square, and then you have what? Summation of fx square by n equals to mu square plus sigma square. You can see here one of the term fx square by n we already have got here. Now let's try for another term. Okay, what is required here now? This, either this or this sort of thing. Okay, x bar square or fx bar square by n. So let's see here what happens. Firstly, try x bar, variance for x bar, and you know that this is sigma square by n, just like that. And if you apply, this is the variable x bar, not the constant x bar. That means if you just use this sort of formula, then it is going to be f x bar square by n minus mean square. Mean, whose mean? Population mean, because this is also based on the probability, this variance is. So it is mu square equals to, you have now sigma square by n. That is finally what you get, summation of, you can write in this form also, this is x bar square and f by n. Okay, this term, and this will transpose to other side. It's going to, it is minus, so it is going to be now plus, so it is mu square, and the sigma square by n is here, sigma square by n is already here. Okay, so now we have available both the values. One values like what we have, this. Okay, fx square by n, you can see here fx square by n value already got. And then another value is x bar square f by n. So you have another value as, you can see here, x bar square f by n equals to this term. Okay, now just replace this term by the new term of here. So from here, EV equals to expectation of, what can you write for this? Mu square plus sigma square. So that is mu square plus, yes, sigma square. And then you have, what is here? Minus term. So minus summation of, what is it? Yes, for this we wrote. For this term, what you can write here? This. So it is mu square plus sigma square by n. Alright, let's go further. So what you see here, because now mu and sigma term both are the constant term, and when you find the expectation of any constant, for example 2, this is 2. Any constant b, it is b. So what you write for this, in that case, it is mu square plus sigma square minus, open this bracket, this is sigma square, minus time plus is minus, this is sigma square by n. Alright, now cancel the like terms. You can see here sigma square and sigma square, they got cancelled out. So what you are left with now? Sigma square minus sigma square by n. Now take sigma square common, so you will have here 1 minus 1 by n sigma square, and then you will have here, after this term, if you take the LCM of this, so n minus 1 by n sigma square. Now what do you think here? It is just like the sample mean and estimator of the population mean? This is obviously no, because if EV equals to you would have got only sigma square, then you could say the sample variance V is the unbiased estimator of the sigma square. But in this case, we see that there is difference by n minus 1 by n. In that case, we cannot say that the sample variance is the unbiased estimator. In fact, this is the biased estimator of the sigma square. But you can see the terms are very close. Even though this is the biased estimator, if you can just adjust this number, you can easily find the population variance by using the small sample data, or by using a very part of the population as the sample data. That is the variance of the sample data. So in that case, for example, let's go further one step more, one or two steps more. So after this, look at here now. If I transfer this to another side, this constant term I'm talking of, so it is divided, so it is multiplied here, then this is multiplied, so divided here. This is expectation of V equals to sigma square, and after that, what is expectation of n minus 1 V equals to sigma square. You can now say not only the sample variance, but the sample variance with this factor is the unbiased estimator of the population mean in this case. Okay, so what you can say after that, like you can say sigma square estimated value as n by n minus 1 V. That means the estimated in order to estimate the value of the population variance, you have to multiply by the sample size divided by sample size minus 1 to the sample variance. This is also possible that you can just apply the formula of this n by n minus 1, and you know that the variance is this sort of thing. Yes, 1 by n summation of x minus x square in the sample form. So this is the sample variance. So what you can write? Times 1 by n summation of x minus x bar squared for the individual series. If it is the discrete series, we can also apply f, where n will become summation of f. Now you can see the n in the, where is it? Yes, this is up to here. Yes, n by n minus 1. So n and n dot cancel out. So what we are left with then? We are left with, after that, only in the denominator 1 minus n. So it is 1 minus 1 n 1 by 1 n minus 1 summation of f x minus x bar squared, if I am considering this as the discrete series. If this is the individual series, just remove f, then that will give you the value. So it is easy to calculate, although the sample variance is not the unbiased estimator of the population variance, but it is simple to calculate the value of population variance based on the sample data in this way. And this formula you can represent in different way. For example, one of the ways like this. Okay, so this explains that how we estimate the mean and the variance of population by using the sample. Okay guys, this is all for today.